Alright, so in this video we're going to build a little bit on the idea of span. Remember, span of a set of vectors was the set of all possible linear combinations of that set of vectors. And the question is, if you take a set of vectors, take their span, are all those vectors necessary? Is there a minimal set of vectors that we can use to create the same span? Well, here's an example. Here's a plane and we have three vectors in the plane. Now, in fact, the plane is the span of any two of those vectors. You don't need the third one. So any two of those vectors would be a minimal set that would span this subspace of the plane. This minimal set is called a basis, and the property that makes it minimal is called linear independence. So we'll get more into that as we go. All right. So you can see here that the fact that one of these is not necessary can be expressed in this way, that W is a linear combination of the other two. So if W is a linear combination of the other two, I don't need W to make any further linear combinations. Any linear combination that involves W, I could replace that W with D1U plus D2V and get a linear combination of U and V. So I don't need W to create additional linear combinations. I can reduce any linear combination with W to a linear combination with U and V. All right, now you can rearrange this equality here and put W on the right-hand side, and you get 0 equals minus W plus D1U plus D2V. So in fact, you have something like this. You have 0 is equal to a linear combination of these three vectors. And that means that one of them is not necessary. In fact, if you have an equation like this, and for instance C1 is unequal to 0, then you could bring the other two terms to the other side, divide by C1, and you would get U in terms of V and W. So the U is not necessary. It's expressed in terms of V and W. So let's generalize this definition. If we have a set of vectors that can form a linear combination that gives 0, we say that these are linearly dependent vectors. And as I said, that means that at least one of these vectors is not necessary in forming linear combinations. In fact, the 0 vector can never be on a list of independent vectors, because if I multiply 0 vector by any constant, it's still 0. For instance, if V2 were the 0 vector, I can make C1 be 0, C3 be 0, Cn be 0. I can make C2 non-zero, and I still get 0 here. Now notice here that the linear dependent means that there exist constants C1, C2 up to Cn, not all 0. You can have some zeros, you just can't have all zeros. So the example I just gave, if V2 was the 0 vector, I could have 0V1 plus 5 times the 0 vector plus 7V3 equals 0. That is a linear combination. So that's a non-trivial linear combination because the second coefficient is not 0. So in that case, any set of vectors that has the 0 vector will be linearly dependent. All right, so let's look at this example. If I have 1, 2, 3, 4 vectors here, are they linearly independent? As it turns out, it doesn't show you how you got this result, but in fact, you can work out that 3v1 plus 2v2 minus v3 plus v4 equals 0. This is a linear combination of the 4 vectors. It turns out to be 0. So the vectors are not linearly independent. The vectors are linearly dependent. So the question is, how do you show that in general? Here they just did it. They told you, it's kind of like magic. Now how do you show that systematically? Right? Well, let's consider this example. Suppose we have these three vectors. Are they linearly independent or not? Well, if they're linearly dependent, I can form a linear combination and get 0. Now, if you think about it, this is actually a system of equations in 3 unknowns, C1, C2, and C3. It's a homogeneous equation because the right-hand side is 0. So I can recast this as a matrix vector equation. The v1, v2, v3 are column vectors. So this is a 3 by 3 matrix. This 3 by 3 matrix times this 3 by 1 column vector equals 0 expresses this same relation. Okay, we've seen before that a linear combination of vectors, some vector equation like this can be reduced to a matrix vector equation. Right? And the only way you can find a solution to this is if the matrix v1, v2, v3 is singular, which means that the determinant of this matrix would have to be 0. So the condition that v1, v2, v3 is linearly dependent reduces to a condition on the determinant. And in fact, the determinant of this matrix is 0. So that means that v1, v2, v3 are linearly dependent. Okay. So at this point we might ask, can we find a specific relation of linear dependence? A relation of linear dependence would be explicit coefficients c1, c2, c3 that makes this 0. Well, you're just solving a homogeneous equation, which we've done before. Just take your coefficient matrix, row reduce, find the REF. Here's the REF. Here you've got one free variable and 2 pivot variables. So you could set your free variable equal to 1. If you set your free variable equal to 1, that determines the dependent variables. And for example, and you get the general solution here. And go back and review how you use the REF to find general solution of homogeneous equation. Right? So we can in fact get minus 2v1 minus v2 plus v3 equals 0. In fact, we could multiply each of these coefficients by 3, 5, 12 square root of 9, or square root of 19 or something, and still get a linear dependence relation. Right? All right, so here we have linear combination, linear dependence. An order set of non-zero vectors is linearly dependent if and only if one of the vectors is expressible as a linear combination of the preceding vectors. This is kind of what I referred to up here, was that in this case you had W equal to d1u plus d2v, and you can bring, and this is basically can be reduced to this form. So if W is expressible in terms of the others, that means that the 3 are linearly dependent. So you can look at this two ways. You can say that vectors are linearly dependent if there is some kind of linear combination that gives 0, or you can say vectors are linearly dependent if one of the vectors is expressible as a linear combination of the others. Okay. And basically what you do is you look at the relation of linear dependence. One of the coefficients must be non-zero. I can solve for that corresponding vector in terms of the others. Right? On the other hand, if one of the vectors is expressible in terms of the others, I can turn that into a linear dependence relation. That's what this is saying. So you can read through this proof in detail. But just the point is that there are two different ways of looking at linear dependence. One is saying that a vector is a combination of the others. The other is saying that the combination of all the vectors can give you a 0. Now, I talked about showing linear dependence. Showing linear independence is going to be a similar process. Remember that to show linear dependence, we reduce the problem to a homogeneous system of equations. Well, that's the same thing if you want to check linear independence. If I want to check if these three vectors are linearly independent, that's the same thing as this vector sum equation, which I can reduce to a matrix equation. And we happen to know that this homogeneous system has a non-zero solution if and only if this matrix v1, v2, v3 is singular. Okay? So if v1, v2, v3 is non-singular, the only solution to this homogeneous equation is c1 equals 0, c2 equals 0, c3 equals 0. What does that mean? That means there is no linear combination of v1, v2, v3 that gives me 0. All right? So all I have to do is check the determinant. The determinant is non-zero. That means that this matrix v1, v2, v3 is non-singular, and the vectors v1, v2, v3 are linearly independent. As you can do this other example, similar argument. Okay, now we talked about in span of vectors finding a minimal set of vectors that have the same span. So in this section, we talk about how you can take a set of vectors that's not minimal and create a minimal set. Now, if the vectors are linearly dependent, they're not minimal because there must be at least one of these vectors that's a linear combination of the others. And I could remove that vector from the list of vectors. So, for example, if I have this linear dependence relation, and suppose C1 is not 0. Now, C1 was not 0. You just rearrange the vectors so that the first coefficient is non-zero. Right? So if the first coefficient is non-zero, then V1 is a linear combination of the others, and the span of V1 through Vn is the same as the span of V2 through Vn. V1 is redundant. Okay, so and then I can do the same thing with V2. Okay, then I can look at V2. If V2 is linearly dependent, if the V2 through Vn is linearly dependent, then I form that linear combination, find a coefficient that's non-zero, solve for that vector, and remove that from the list. Okay, for instance, if V4 equals V1 plus V2, then we don't need V4 in the list. So we can remove that. We can just use V1, V2, V3, and that will have the same span. And what you have then finally is a linearly independent set of vectors that span the subspace, that span a certain subspace. And this linearly independent set that spans the subspace is called a basis. And we'll be talking more about that in subsequent chapters.